In this lesson, we're going to look at matrix operations, and we're going to start with what a matrix is and some of the matrix definitions so that you're clear on that. And eventually, we're going to use a couple of different methods whereby we use matrices to solve systems of equations. So we're going to start with section 9.3, some definitions and some operations. So a matrix is a rectangular array of numeric or algebraic quantities subject to mathematical operations. So it's a rectangular grid of numbers, and those numbers need to be in a specific place because that place represents something real, okay? So the size or order of a matrix is given as rows and columns. So for instance, matrix A here has 3 rows that you can see. So it's a 3 by 2 matrix. Okay, so we count the number of rows first and then the number of columns. And B is 3 rows, 3 rows, 3 columns. So it's a 3 by 3 matrix. When the number of rows is equal to the number of columns, we also call that a square matrix. Okay, and we use capital letters to name our matrices, and we use lowercase letters to describe one of the elements or numbers that it's in the matrix. So if you look at matrix A, the element that's in row 2, column 1, is a 7. In matrix B, the element that's in row 3, column 2, is a 9. And in B, row 2, column 3, is a 1. So it's important that you recognize that the lowercase matches the matrix and that it goes row first and then column. Okay? Now, if you look at matrix C here, we call that an upper triangular or a triangular matrix. And notice that everything above the diagonal has some values, and everything below the diagonal is zeros. Okay? And matrix D here is called a diagonal matrix because everything except for the diagonal is zeros. The importance of those will come up later when we start solving linear systems using matrices. Matrix E here is a special kind of diagonal matrix where the diagonal is filled in with ones. It's called the identity matrix. And this happens to be the I3, which means it's a 3 by 3 identity matrix. I2 would be the 2 by 2 identity matrix, which would look like this. You can have I4, for instance, which will be a 4 by 4 identity matrix, where you've got 4 ones along the diagonal and everything else are zeros. Moving along with our definitions, 2 matrices are considered equal if they are the same order. So that means their size or dimensions have to be exactly the same, and if all the elements are equal in the same locations. This is also important, okay? So equal size, equal elements. So if I look at matrix A and matrix B, I have the same elements in the same locations, but they are not the same size. So A does not equal B. if I look at A and C, I have the same dimensions, I have the same elements, but they're not in the same places. So A is also not equal to C. They have to be equal size, same elements in the same locations in order to be considered equal matrices. Here's an example of a question that we can answer based on the knowledge of equal matrices. If D equals E, in other words, if matrix D equals matrix A, find the values of X, Y, and Z. Okay, so if these matrices are equal to each other, we know that X plus 2 is in the same location as 5. So X plus 2 must equal 5. We can see that 2y is in the same location as negative 1, so 2y must be equal to negative 1, and 7 in D is in the same location as 3z in matrix A, so 7 equals 3z. Okay, so we can solve each of these and say that x must be equal to 3, that y must be equal to negative 1/2, and that z must be equal to 7/3. And if those are true, then those two matrices are equal to each other. Matrices can be added and subtracted, but again, this can only be done if they are of the same order. Okay, so the size, the dimensions have to be exactly the same. So for instance, I have here matrix A, which is a 3 by 3 matrix. B is a 3 by 3 matrix. C is a 3 by 2 matrix because there are only 2 columns. So we can find the value of A plus B. And what we do is we just add the elements that are in the same locations. So element row 1, column 1 is 1, and negative 3, we can just add those together. So we'll have negative 2, 11, 3, 6, 12, 22, 0, 9, and 18 as our solution for A plus B. Let's add A plus C. Hopefully you're saying, no, we can't do it, which is true because this is 3 by 3, C is a 3 by 2, so this is undefined. And that's what we write when an operation can't be done because it doesn't, the requirements for that operation aren't being met. We just say that it's an undefined, that the solution to that is undefined. Let's try A minus B. Again, the solution for adding and subtracting, because we're working with two matrices of identical size, the solution is also of the same size. So if I do A minus B, it'll be 1 minus negative 3. So do watch your signs there. So that'll be 4, 3, negative 7, 4, 0, 0, negative 4, negative 7, and negative 6. And again, if I were to say, well, what about B minus C? And again, that's another one that's undefined because they have different orders or different dimensions. So that's addition and subtraction. Multiplying matrices comes in a couple of different methods, and in this lesson we're going to look only at the first method, which is scalar multiplication. That means we're multiplying a matrix by a real number. We're not at this stage yet multiplying a matrix by another matrix. So when we do scalar multiplication, we multiply each element of the matrix by the real number that we're multiplying. Okay, so we could say that, for instance, negative 3c, and we'll use a, b, and c from the previous example. We could say that negative 3c is equal to, we just multiply each of the terms by negative 3. So we'll get negative 3, 6, negative 18, negative 15, negative 21, and negative 9. We've multiplied each term by negative 3. So we could also do something that's slightly more complicated and say, well, what's 2a plus 3b equal to? And I forgot to use capitals there. Well, we can multiply matrix A by 2. So we're using the scalar multiplication. So we have 2, 14, and negative 4, 10, 12, 22, negative 4, 2, and 12. And we're adding 3b, so that'll be plus, and let's multiply each element in b by by 3. So we get 9, 12, 15, 3, 18, 33, 6, 24, 36. And now we can add those together and get our result. So we can say that's equal to negative 7, 26, 11, 13, 30, 55, 2, 26, and 48. And finally, for this lesson, we're going to solve matrix equations. So I have a matrix equation here of 2x minus a equals b, and I want to solve for x. And I'm using a capital X because x is a matrix that I'm solving for. The first step in solving these is to rearrange the equation before we put any numbers in. We want to isolate the x. So 2x will be equal to matrix A plus B, and x will then be equal to, and rather than dividing, B plus A, rather than dividing, we will multiply by the reciprocal. We'll multiply by a half. Okay, so that means x is equal to 1/2 of b plus a. So x is equal to 1/2 of, and I'll get b and a written down here, negative 3, 4, 5, 1, 6, 11, 2, 8, 12, plus 1, 7, negative 2, 5, 6, 11, 2, 1, 6. So now I can add those two matrices, A plus B. So I've got 1/2 times, and actually I don't need that round bracket anymore, of negative 2, 11, 33, 6, 12, 22, 4, 9, and 18. So if x is 1/2 of that, then x is going to be equal to, and I just multiply each of the elements by 1/2, so I'll get negative 1, 11 halves, 3 halves, 3, 6, 11, 2, 9 halves, and 9. And we're finished. Next class, We will look on matrix multiplication, the conditions whereby we can multiply one matrix by another matrix.